I begin with three observations. First, despite breathtaking empirical progress, our mathematical grip on how large language models reason is still very partial. Even the chain of thoughts technique, today's work source technique, is more heuristic than theory. So mathematical theory of large language models is still fragmentary. Current theory explains only slices of LLM reasoning, robustness, or safety. Missing pieces include compositional generalization, chain of thought correctness, avoidance of hallucinations, or out of distribution robustness, and many other things. As a result, architecture design or diagnostic tools are largely empirical, and theoretical guarantees are scarce. So why topology? Why topology can help? If we look at very remote mathematical and not only mathematical domains, topology have stepped in to explain deep principles behind different things. And this story is really very surprising. So, for example, in mathematical physics, topological quantum field theories underpins particle physics, string theory, explains many phenomena, condensed matter physics, and is fundamental for quantum information. In very remote subject, number theory, the topological invariant, the arithmetic genus is ubiquitous. In analysis, mass theory links critical points to local and global behavior of various functions. So all these subjects, if one looks at them, are very, very remote from each other. Nevertheless, topological ideas, topology plays important, essential role in all of them. Very remote subject. In logic, topological semantics via Stone-Tarski duality bridges Boolean logic and topological spaces. And this set of ideas was developed to a much further extent in so-called topos theory. Homotopy type theory provides a foundation for formal proof assistance. And if one looks at people who contributed into these various successes of topology, the list is very expressive. It's very impressive. Right? It started with earlier Poincaré, Riemann, then many people contributed, like Chern, Atiyah, Grothendieck, Voevodsky, and many others. So all of them are like the brilliant, one of the most brilliant minds of their time. Why such universality? Why topology is so pervasive? This is a deep question to one can reflect upon. Perhaps topology reflects our intuitive notion of connectedness, emptiness, or stability under deformation. So this is some kind of deep intuitive notions that underlie many cognitive processes in our brain or in general. So some cognitive studies support the resonance between these topological notions and human perception or human way of thinking. But this is still mysterious, why topology appears again and again in different subjects. That is why the appearance of topology in mathematics of large language models and large language models reasoning is very inspiring. So let's have a look at most prominent places where it appears. This list is not by no means exhaustive, but I think all of these points are very essential for our understanding of large language models reasoning. Okay, so we'll start with intrinsic dimension, which can be defined purely in topological notions, intrinsic dimension of data representations. And I will describe application of so-called persistent homology dimension to the detection of AI-generated text. Next, I will speak about how the topological notion of graph topology divergence has been recently applied for hallucination detection. Next subject brings back the logic topology duality that I already mentioned, which did not yet play a prominent role, but it has already appeared in several works, several interesting works on large language models reasoning. And we'll have a look at this logic topology duality, which is a very deep subject, and how it is now applied to enhance reasoning on knowledge graphs, these large language models. Next appearing subject is homotopy-inspired proof generation. So this is also related with what I already mentioned. And I finish by rather more elementary approach, comparing two weighted graphs using topological divergence in order to to make comparison of data representations, but it still hints at some mysteries that are very interesting to study and to resolve. Okay, this is the plan. And I will speak about several topological tools. Some of them are more elementary, others are more compound. And the aim, if you wish, while you will be learning probably new material or some material that you already know, some thesis at this summer school, one can try to use your intuition deeply related with topology and perhaps apply some topological methods, simple or more complicated, to improve our mathematical understanding of large language models. Okay, so I start with intrinsic dimension detector for AI-generated text. The principal thing here is minimal spanning tree. So topologically, minimal spanning tree describes the evolution of connected components across different scales. So typically, we are given a mathematical definition as follows. We apply it to a point cloud of data representation, typically from the last layer of large language model. So if we have a point cloud, we can form a connected weighted graph. The weights are given by in this case, the weights are given by the distances in the ambient space. Or it can also be used with other distances like geodesic distance and so on. So given a connected weighted graph G, consisting of set of vertices, set of edges E, and the weights W, minimal spanning tree is a cycle-free subset of edges, a tree, that connects every vertex and minimizes the total weight. This is a basic notion. There is a well-known so-called, for example, Kruskal algorithm that computes it, and it's basically looks at all edges one by one, ordered in their weight, starting from the smallest, and adds the set of minimal spanning tree, the edges that connect different connected components up to the given scale. Okay? So just looking at this algorithm, we see that it describes how the connected components evolve when we starting from the small scale. We add only small edges, so there are a lot of connected components, and adding bigger and bigger edges, these connected components they become united together, and this evolution is described precisely by the length of the minimum spanning tree edges. So what one can do is to do the following thing is to take the total length of the minimum spanning tree, total weight, and some result about random points in d-dimensional space predict that the total length of the, if we take n random points, total length of this minimum spanning tree would behave as follows. It would be proportional to the to n to the power of d minus 1 divided by d. And this forms the basis for an estimator of intrinsic dimension of the corresponding point cloud, or rather underlying manifold on which this point cloud is supposed to lie. So what one does, one computes this total length and then constructs a linear regression between the logarithm of the total length and the logarithm of the number of points. And then the dimension is given by the formula 1 divided by 1 minus alpha, where alpha is the slope of this linear approximation to the total length. So this is how this is computed, and very interestingly, with our colleagues, we found that if one takes, for example, representation of Roberta language model, puts some sentences from different datasets, and it turns out that the human languages in this dataset, human texts, typically have dimension around 9 or 10, and AI-generated text typically have somewhat small dimension. About the difference is about 1. And similarly, very interestingly, this happens all across languages. So it doesn't depend on the language. The only thing that depends on the language is that if we use alphabet-based language, then the dimension is closer to 9, and for Chinese or Japanese character-based language, the human dimension is around 7, and AI-generated text is a little bit smaller. So this was calculated for the GPT 3.5. Some of this remains true for GPT-4 and for the models. And our detector accuracy was quite good. If we take single threshold Ruka at 0.94, and most surprisingly, that was robust across different models and domains, also language agnostic. So, takeaway point, a single topological statistics can detect AI-generated text. Right. But intrinsic dimension is actually, first of all, again, from the point of view that we approach is a topological notion. It's about how the points are connected at different scales and how this connectedness behaves as scale grows. This scaling, this intrinsic dimension appeared in the context of very important other works like scaling laws for large language models. For example, in a preprint around 2020, Kaplan and collaborators showed that empirically test laws for large language models falls as the exponent with proportional to the number of parameters. And this beta, they argued, this is empirical study, and they argued that this beta is related somehow with intrinsic dimension of the data representation obtained by this language model. So they propose the formula that beta is proportional to C divided by D with C equal to 4, and gave some initial the toy model arguments for this formula, and then other authors continued this very important line of study and gave some more arguments for this formula, assuming that we have data that lives on a d-dimensional manifold, supported on d-dimensional manifold, then indeed there are strong theoretical arguments supporting this behavior of the total of the loss according to this law. Similarly, the compute optimal frontier was established by other authors. They define the token per parameter ratio, the optimal point shifts with intrinsic data dimension. More recently, authors like Avila and Leao in 2024 fit the GPT-2P TR1s to obtain beta values that match again this C over D across different tasks. So all these works were partly empirical and also gave further and further theoretical support, but still there is no full understanding why we have this scaling laws. Other people started to apply this technique to study what happens on different layers of the transformer models, like depending on the depth of the layer. Some authors found that this intrinsic dimension is estimated with minimum spanning tree start to climb towards the middle of the layers, and then final blocks compress back to some smaller dimensions. Also for larger models, this collapse to smaller dimension happens more in a more soft way. So this is also an interesting thing about how the data is travels through the layers of the large language models. Very recent study found that some arguments that reasoning data sets require higher intrinsic dimension, and in particular they theoretically or empirically require up to 6 times more parameters for the same loss than more standard datasets. This is a very important subject, relation between the behavior of the loss with respect to the number of parameters of the model or with respect to the data set total number of points. This can be very easily subject of a separate lecture or even a series of lectures. So this is an active domain. I think it would be very interesting to contribute into this development. So take home, if you wish, this topological notion and increasing dimension is a kind of deal that sets the scaling exponent beta and therefore the compute budget. And if you know how to estimate accurately these intrinsic dimensions, this permits us to forecast the return on the model scale. Okay, so this is probably most application-oriented topological notion that is used up to now. But still there are many things that needs to be done to understand fully what happens. Next topological setup that I would like to describe is graph topological divergence that with our colleagues we recently applied for hallucination detection. So the pipeline is the following. We worked with attention matrices. So attention sits inside every layer and every head of the given layer. We convert this attention scores to weighted graphs. Each token corresponds to a node of our graph, and we cook from the attention score some kind of distance between tokens. So if one token is related by strong attention with another, then these tokens are related in a strong way, so the so-called some kind of pseudo distance must be small on the other hand. That is why we convert the attention weights into some distance weights by the following formula. We take the attention weights alpha ij and deduct them from 1, so that if attention is close to 1, the distance is close to 0. In ideal situation, for example, if there is some set of tokens that are related by attention equal to 1, then all these edges would have weight 0. But otherwise, it is some non-zero number, smaller or bigger, between 0 and 1. So we obtain a weighted graph for each head of the attention model. Okay. Then we do the following thing: we separate tokens that correspond to prompt and to the answer of the model. So we get vertex sets given by the prompt tokens and vertex sets given by the response token. Okay. Then we put the weights for the attention between vertex sets P to 0. We don't want to take them into account in this calculation. And what we do, we compute H0 victorious Reeves barcode, but it is essentially the H0 barcode we have already encountered in the previous approach, namely if we have this graph with sets of vertices P and response R, we have this weighted graph, we can somehow collapse all prompt vertices to a single bigger vertex and see at what is with what force the response tokens are attached to the prompt, right? By a series of attention weights. So it might not be attached directly to the tokens of the prompt, but rather by a sequence of some attention weights. And for this graph, which we obtained, getting tokens with distance given by inverse to attention weights, then collapsing the prompt tokens. We calculate the minimal spanning tree of the resulting graph, right? It would correspond to the minimal spanning forest that attaches the response tokens to the prompt tokens. So we do this topological operation, and again it shows the behavior of connected components, topological object connected components at different scales, and how this behavior of connected components evolves as we increase our scale. And scale in this case is essentially to what extent the attention differs from one, right? So small scale correspond to tokens that have strong attention between them, and bigger and bigger scale correspond to smaller and smaller attention between different tokens. So we look at this again as the evolution of these connected components attached to the prompt. We take total length of this minimal spanning forest attaching R to tokens of the prompt, correspond to the persistent homology barcode total lifespan, the average of the number of response tokens to get a number between 0 and 1, and to be able to compare this in different situations. And then we obtain a per head score, compute this graph topological divergence for every attention head, and obtain the head-specific hallucination signals. So very interestingly, this in fact works quite well. So in particular, in essentially every model, we found some kind of universal hallucination-aware heads, right? So in every model, there are some heads that are able to detect that gather information, the meaning of what's going on, and detect whether by their attention weights and topology of this attention weights detect the hallucinations. So we rank heads on a probe set by the difference between hallucination of hallucinated sentences and ground sentences, and keep the top 6 heads out of much more bigger amount of heads. And very surprisingly, these heads transfer quite well across datasets and also exist for different models. So this is probably the most interesting finding, that doing this, and these the obtained universal hallucination aware heads are work on different datasets and can be found for different models. And then
we have a question. Yes, it's okay to ask a question now.
What?
It is okay to ask a question to you now.
Yeah, if you want, yes.
Yeah, thank you. I want to ask you a question about do you research how many heads remain context aware if the context length is very big? I mean about 100,000 tokens which we observe in modern LLMs. So, and they they cannot use all their context to generate answers. So they are very easy. They can very easy give hallucinated answers. Have you researched LLMs with very big context length or not? Or is this research applicable to such problem?
So this is a very recent paper. This is essentially we put it on the archive this year. Very interesting question. Of course, there's interesting research direction. We did some partial experiments with this respect. So this continues to work as we increase the number of tokens in the prompt. But of course, the model tend to hallucinate more if we include bigger and bigger.
Actually, we will have an expanded version of the slide in my lecture on, I suppose.
Yes, see, we'll describe this.
Experiments and your discussion.
Thank you.
And one interesting thing to mention is that it's quite compute efficient. This is k equal to 6 head design, and it works essentially in a single pass. So when one puts this text into a large language model and immediately obtain the corresponding scores. So it makes this Toho method up to 10 times faster than some other multi-sample detectors. Also, interesting remark is that we, at the same time, we take some interpretability bonus that heavier minimal spanning forest edges highlight tokens that drives hallucination, right, that would correspond to attention rates closer to 0. And then these tokens are not topologically attached to other tokens that are attached well to the prompt. Okay, so it can be attached directly to the prompt, or it can be attached in a good way to other already generated tokens, which were themselves attached by some chain of these attachments to the prompt. So here is the reference, and takeaway is higher GTD score implies weaker context and likely hallucination. My next example is about logic. So there are some works on logic topology duality for reasoning on knowledge graphs. So let me start. This is not yet fully developed with all existing potential, I believe. But there are already some works that try to apply this logic topology duality. So this logic topology duality goes back to works that started in the 30s in the 20th century, in the beginning of the studying of the various logic theories. And let me give you an elementary example of logic topology duality in the case of the propositional logic. Okay, propositional logic is probably you have already encountered in your studying several times because it is used in various digital circuits, verification, and so on. So typically in mathematics or in the computer science curriculum they are studied quite early. But just to recall, so typically it works with atomic or compound propositions. So it's like these are like statements. Atomic statements are assumed to be indivisible and take either true or false value. Okay, there are no intermediate in this simple setup. There are nothing intermediate. Every atomic statement takes either true or false value. And then there are operations that allow to make compound statements out of the atomic statements and obtain more complicated statements. So we use people use 4 standard operations like not, and, or, and if-then operation. They are defined by how they act on the tables of true and false values of the individual atomic propositions. Okay, so there are standard tables. For example, the table for the and, or, everybody. So of course, and not. The table for the if-then is a little bit not immediately intuitively grounded, but it can be argued that essentially this is the only possible table for such an operation. There is standard approach to this, to understanding the true or false value of a given compound proposition via valuation in which each atomic proposition takes either true or false statement, and then the compound formula, which consists of many operations applied in different order to the many atomic propositions. This compound formula also takes either true or false value. And the important question, important problem in this domain is given a very complicated formula which consists, I don't know, of 100 to 1,000 operations on similar number of atomic statements. Can we how to verify that this formula remains always true independently of the atomic propositions? Or, for example, this formula always delivers false value independently of the value of the atomic proposition. Or if this formula has at least one truth value for at least some values of the truth or false value of atomic proposition. All these are standard important questions in this theory. I will discuss how this is typically approached. There are essentially 3 approaches. So one is, I already mentioned, is by forming the table, right? This big table of various values of atomic proposition, and then going through the formula and deciding step by step which value takes the compound formula. But there are two others approaches, and I will describe them in a minute. Also, so one of the approach is to use the proof rules to deduce some tautology starting from other tautology. This is another approach. So this is so-called entailment and proof rules. So essentially, this is a basis of the elementary logic, and for digital circuits and verification and richer logics. So how this is approached? How, for example, verify that some formula is true in all valuations. Okay. So classically there are 3 approaches. One again is a brute force truth table check, another is a derivation by the rules. So some kind of natural deduction given if there are simpler formulas that enter into our compound formula, then by certain rules, so-called Hilbert rules, natural deduction rules, some more complicated formula can be deduced from simpler formulas. This is so-called syntactic approach. And there is this third topological approach, which essentially interprets each atom as a closed and open set into some topological space. And the statement is that the formula, if we interpret each atom statement as an open set, the formula is tautological if the corresponding region to this formula is the whole space for any such representation, right? There is some universal representation which is called stone space, and if in this universal representation or similarly for in any other representation, the region which corresponds to the given formula coincide with the whole space, then this formula is a tautology. So this is topological, in a sense, intuitive way to verify some quite complicated formulas. And this is essentially central for the application of this topology logic duality, right? This interpretation that which starts given a formula in for example, in propositional logic or in more general logics, like first order logic or model logic, one interprets some arguments in this formula as subsets in a topological space, and then make statements about the formula based on the topology of the resulting subset in a topological space. Okay. Very interestingly, this works in other direction as well. So if we have some statement about a logic formula, we can make some statement about the corresponding topological subspace, and if we have some statement about some topological subspace, we can make a statement about the truth, false, or other properties of the given formula, logical formula. So in AI and data analysis, this topological view extends to model fuzzy distributional semantics, which are typically can be approximated by LLM embeddings. Right. So this point of view brings this topology logic duality to the center of studying reasoning. And also it provides a topological intuition for learning systems, and as well as continuous relaxations. Okay, so in Fourier distributional logic, some statement can be true or false with some degree, and this is can be modeled similarly using this approach. So I described only some simple situation with propositional logic, but this can be generalized. So to understand better what happens, let's consider this simple example. Suppose we have this implication transitivity formula, namely P implies Q simultaneously with Q implies R. This implies that P implies R, right? So we all know this rule. How this can be deduced in the three approaches, right? So first approach is the truth table. we have three variables, P, Q, and R. Each takes either true or false value. So we just run over all possible values of true and false of these three variables. It is we see that already just for three variables we need 8 considerations, and if we have 10 or 100, this becomes quite cumbersome, computationally expensive. But in this case can be easily verified. There are just 3. Similarly, we have a rule-based deduction. So if we assume P and the antecedent, namely the formula P implies Q and Q implies R, assuming P and this antecedent, we can deduce it that given P and P implies Q, we obtain Q. Given Q and Q implies R, we obtain R. And this is precisely what we need to deduce, to conclude that P implies R. Right? This is a rule-based deduction. So again, very simple in this case. For more complicated compound formulas, this is much more complicated. But intuitive approach to the topology, in this case, also works quite well. So we have 3 sets: CPU, CQ, CR. They are suppose they are simultaneously open and closed in some space. Implication P implies Q is modeled by the union of the set corresponding to Q and complement to the set of P. This is denoted by C and with C subscript. So the antecedent region can be modeled by the intersection of the corresponding regions for each subformula. And if one draws these sets, one easily sees that it is contained in the set complement to P and CR, union with CR. And using some manipulations with subsets. So it follows that the region of the whole formula corresponds to the full space, and this is a tautology. So this gives a third way to deduce, to understand the tautological formulas. Take away that all 3 possibilities confirm the validity of this formula, and the topological proof visualizes or gives an intuitive explanation how the truth flows through the open regions. In a sense, prefiguring how topological geometric reasoning can be studied in narrow embeddings. This logic topology correspondence is already used for understanding reasoning over knowledge graphs. So there are this is I believe in the beginning of the application of this duality. In particular, topology logic duality inspired approach inspired some probabilistic soft closed open embeddings for knowledge graph reasoning. So the entities for this reasoning and arbitrary queries are encoded as distributions in these approaches, as distributions with some standard distributions with some parameters, and then operations on these distributions correspond to transformations on these parameters. So the operations like existence and or negation act directly on distributions. And this gives a kind of embedding model that supports all first order logic, for example, in the case of the multi-hop knowledge graph reasonings. But this is still at the very beginning. It is not clear to what extent this is the most optimal way to construct these embeddings and so on, and how to how to find these embeddings, perhaps inside large language models. So not to construct these embeddings by some specific setup, but whether it is possible to find this natural embeddings in existing between existing embeddings inside the large language models, or maybe combine some embeddings to produce this. All this is very interesting, very deep questions that is a natural way to understand, to improve our understanding of mathematics of large language models. So next I will briefly mention the homotopy-inspired proof generation. So this is goes back to the works initiated by mathematicians in order to construct formal proofs systems. Two currently most popular systems are Lin, Coq. Well, there are some others, and topology in the form of homotopy type theory. It extends in a natural way these systems and gives many important and useful properties of these systems. In particular, it gives a principled identification of isomorphic objects inside this formal proof assistance. It also has built-in quotient types, because we, in the proof assistant, mathematical concepts many often involve some kind of quotients. So this homotopy type theory has them intrinsically in a very interesting way. And also it provides a growing stock of already formalized mathematics. So the main problem in this, one of the biggest obstacles for application of transformer models to produce automatic proofs is the lack of sufficient number of interesting formalized proofs. So this homotopy type theory in particular provides a growing stock of this reusable formalized mathematics. And very recently, by having LLM-driven tactic generation into Lin4, extended by this homotopy type theory, and Coq, extended by homotopy type theory kernels, so interestingly, that one automates about 40 to 50% more proof steps than classic rule-based solvers, while still letting, of course, the kernel verify correctness. So this is a work called by CPR. This is a planner executor and pipeline, and essentially, interestingly, it using this HOTT approach, homotopy type theory approach, this permitted essentially double the automatic proof success rate in the case of Coq HOTT library. Now I turn to more a little bit more linear tree approach. So essentially, this is a formalism that we developed with my colleagues over this since several years. What is called the topological divergence for representations comparison. Okay, so we already encountered some topological divergence which distinguish graph from its subgraph, and this is a different setup, different situation. In this case, we have 2 point clouds or 2 weighted graphs, and find one-to-one correspondence between vertices of this graph. So one can think of the situation as if we have some data points corresponding to vertices, and this data has two different representations in two different ambient spaces. Okay, and one up, for example, like here we have two domains. One representation is pictured here. Another representation is pictured here, and we have two weighted graphs given by the distances in each ambient space. So these two representations can have different structure, and one of the simplest structures is clustering at different scales, and how this clustering evolves in both cases. So in particular, in this case, we see that at some small scale, in one representation we have 3 clusters. On this 6 points, 1, 2, 3, 4, 5, 6, there are 3 pairs which sit in the same cluster, and 3 clusters in total. And in the second representation, we have 2 clusters. The points 1, 2, 3, 4 sit in the same cluster, and 5, 6 in a different cluster. Okay, so this is a very elementary example how this representation topology divergence is defined. So basically what we do, we form the graph which consists of the union of the edges of these two graphs, and compare the topology of each graph with the topology of this union, right? And then this can be done by some standard topology method, namely the map between the zeros homologies at a given scale. But then we increase the scale, and this map evolves. So there are different situations that tells us that some clusters become joined when we add more vertices, or on the contrary, in some representation they also become joined, but not in the other representation, and so on. So this evolution of the map between each of the graphs and the graph consisting of the union of the edges is precisely what is described by this representation topology divergence. So let me go to a more formal description. Oops. So we try to compare two representations of the same data, 2-point clouds with one-to-one correspondence, and we construct certain cross-bar code for 2-point clouds lying in a different space. This is our reference to our work with my colleagues, representation topology divergence and method for comparing near and near-equivalent representations. So we construct the barcode. In this case, what is this barcode? Barcode is a set of segments, and each segment has appearance point and disappearance point. So in this case, this barcode consists of just one segment. It corresponds to its left end corresponds to the scale at which this cluster of 4 points is formed. So this smallest segment which unites these 4 points into one cluster. And in another representation, we don't have this structure. We still have 3 clusters. So we obtain this discrepancy, and it survives until the scale in which the corresponding edge in the second representation unites the 2 clusters. Okay, the cluster 1, 2, and the cluster 3, 4 become one cluster, and this corresponding edge is this 3, 2 edge between 2 and 3 points. So this discrepancy disappears at the scale 2 omega 2,3. So we have this bar. In this case, the barcode consists of just one bar. It's a very simple situation, almost never encountered. Typically, we have many bars that describe the topological discrepancy between two clusters. And each time they correspond to some kind of different distribution of the points of our data set into clusters at different scales. So this is a situation with H0, zero-dimensional barcode, and it's already very interesting, has interesting applications, but it also can be extended to higher dimension to describe not just clustering, but what happens inside each cluster, some kind of holes existing inside each cluster. And to what extent these holes are reproduced essentially the same place in another cluster. So in contrast to most existing approaches, this RTD is sensitive to differences in topological structures, like cluster voids, some kind of cavity or tunnels inside our representations. Like in this example, we considered points which lie on a circle, but also clusters along several clusters on this circle. All standard methods that compare these distributions fail to distinguish. Like the most standard is CKA method. It is widely used, but if we look at its behavior, it's really rather chaotic in this situation. Similarly for other methods like SVCCA, and our method reflects quite well what happens, that the increase in some kind of topological complexity of this situation, and more importantly, it distinguishes each instance with respect to another instance, right? We compare it, for example, with a single cluster. Here the barcodes are presented, so these sets of segments that distinguish one representation from another representation. In this case, a representation in which there are several clusters, and a representation in which there is only one cluster. And here we see that we have long bars. One can check that, well, there are exactly the number of different clusters that distinguishes the situation, right? So here there would be one long bar, here 2 long bars, 3, and so on. So let me give you the formal definition of this course. So I described it in a kind of hands-down elementary example or more complicated example. So we have a sample of data V. We construct 2 representations with 2 weighted graphs with the same vertex set, and we have wedge 8s, right? The idea is we kind of use these weights to obtain a simplicial approximation to a manifold on which these data points are supposed to lie. So given a threshold alpha, we take all possible simplices with vertices from this set of simplices whose edges have lengths not exceeding alpha, right? So this would correspond to some kind of, for small alpha, typically this would form some kind of simplicial approximation to the underlying manifold. And we compare these 2 manifolds by this topological method. So typically we we track the fact that the simplices which exist in one representation and which are absent in a second representation, when these simplices start to form some kind of non-trivial topological features like paths or membranes and so on. And we track the appearance, disappearance of these situations. So for zero-dimensional, it would be a clustering, but for high-dimensional, there will be some kind of membranes or voids that are formed in each representation. In the examples, we typically use zero-dimensional and one-dimensional, but there are cases in which two- and three-dimensional features are important. And the longer the lifespan, the longer the length of this topological feature, the bigger they described by this feature discrepancy. So to do this calculation, we form the following matrix. So we have these matrices of weights. We form the block matrix consisting of blocks of minima of minima of the two weights. So we form the matrix with twice bigger number of entries, and we essentially put this matrix into standard platforms that compute barcodes. Then the outcome would be a set of segments that represent appearance and disappearance of topological discrepancies between these two representations. So here are the blocks that we use. So here is the minimal block, the block by W, and there is upper triangular and lower triangular version of W. And there are also some specific rows that we use that correspond to some ideal point in this situation. So this is description in terms of Yatori-Rips complex of this. And for those of you who some encountered for some topological notions, this barcode in fact describes what happens inside some kind of exact sequence. So it consists of vector spaces that describe various homology at different scales, and they're related by some natural maps between them. And these barcodes, they essentially sit in this piece, R alpha of G hat graph. And the various homologies have this property that kernel of this map coincides with the image of the previous map. And this permits calculations and various statements about the homologies in this case, in particular for zero-dimensional, but for high-dimensional. So this is the most important theoretical property of this representation topology barcodes. Here are some examples of the calculation. So another example, suppose we have several circles sitting on our distribution sit on several circles, concentric circles. So we can try to compare using this approach several circles with just one circle. And again, our approach distinguishes these distributions, and other approaches typically consider that something random things happen, like CKA, first it drops, then it goes up, and so on. And also as VCCA, there is some chaotic behavior. But cross barcode permits to distinguish this situation. So not only it distinguishes well what happens with clusters, but also with some kind of one-dimensional topological features inside our data sets. This can be important in various situations. And you don't have necessarily to have these concentric circles in your data set, but what is typical situation is that the some parts of the data set can be connected by certain paths with other parts, and these connections are already well, this one-dimensional paths between different kind of boundary conditions for our data set, they are well detected by this method. So this is more common situation when you don't have this cyclic features, but rather different paths between boundaries features, and this is very well detected. And again, with the example of the calculation of the barcode, we see that the number of long bars correspond precisely to the number of non-trivial one-dimensional features that distinguish given data set from the data set in which there is just one such feature. Here we applied this approach to look at the internal similarities of neural network layers. So we clearly see that there is some kind of block structure, right? So we have several layers in this experiment, and this RTD actually reflects much better the block structure inside this neural network than other methods, like one CKA or SVCCA. They do not have such a clearly related picture with the architecture of the network. And this is the example with which I want to finish. And this is really interesting, not very well understood experiment. So in this case, we considered our representation topology divergence. In fact, in this case, one can only concentrate at the divergence describing discrepancies in clustering, also on zero-dimensional features and the discrepancies between them. And the two representations that we take are as follows. We compare representation after the is epoch and the final representation, right, after the training is finished. So towards the end, we have, of course, zero discrepancy because the representations are the same. But along the training, we have some curve of differences of representations. And this is all representation taken from the last layer. In this case, we take VGG network and the ResNet network, but this is typical situation for many different networks. And remarkably, we compare our score, the typically topological score, with the purely probabilistic measure, right? Purely probabilistic measure, namely the model disagreement. So we compare difference in the predictions, essentially. So we use the fraction of mismatched predictions calculated by this simple formula, where we have this class label predicted by network for the given input, right? And remarkably, there is a very strong correlation in this case of this topological measure. So in this setup, this topological measure correlates with this model disagreement. And we don't, it would be interesting to develop some theory that would explain such a strong correlation for these two metrics that come from very different domains. And nothing like this happens for CKA or other metrics. So I would like to finish on this thought-provoking example. So if you have questions, please ask.
Thank you for your presentation, and I have a question. Did I understand correctly that this barcode method works for representations with the same dimensionality? And if yes, then is it possible to compare representations with different dimensionalities with this method or some modification of this method? For example, if I want to compare representations from two different LLMs which have different embedding dimensionality.
Of course, this method was designed to work for representations of different dimensionality. Yes, yes. So it can compare representations obtained from different networks. Yes. And this is a very interesting direction. You know, there is a series of works which tells about universal representations, saying that surprisingly representations of some data which are obtained from in a different tasks by different models can be related sometimes by just some orthogonal transformation or some other transformation, but they are very similar. And this approach can verify this or study this phenomenon. Yes.
Thank you. I also have one question about internal similarity of neural networks. You showed us pictures and they were rather symmetric, maybe because you compared on UNet-like architectures and the ResNet. Have you studied some other maybe asymmetric architectures, and are the layers have some interesting patterns?
You mean this picture? In this case, this is by definition, because when we have two representations, when we have our score, so we have for our barcode depends on the order in which you put these representations into the method. But when we take the numerical characteristics, namely the total length of the bars, we sum all lengths, typically we take half sum of this total length for one order of representation plus the half sum with the order inverse, so that we obtain a single number. So in this case, this is what is presented, and that is why it is by definition symmetric, because we have two representations, right? When we exchange the order of the representation is the same.
Thank you for the presentation. I have a question about, so for example, we have two different neural networks, and we can understand that it's somehow topologically are different. They have the divergence, and what information, what it gives us, how we can use this information, for example. So we understand that two neural networks are topologically different, and for example, how we can use it, how we can use this information, what it gives us.
It depends on the context. We gave some example in our paper. So one can infer various. So this typically works in the same way as the measures of similarity of representations work. So there is this probability theory based CKA method, so that which verifies that for example two representations which are obtained via in a text domain, or the same kind of objects obtained in the visual domain, to what extent they can be aligned, they can be to what extent they are similar, and so on. So this is one typical example when you have you want to compare representations from different modalities. Or like in this example, you can also track what happens with representation along the training. If one sees that there is no longer much difference so you see that, for example, here the training was essential. At the end, there was some drop in the similarity. But if this zero score would be obtained earlier, so we can say that we could just simply stop earlier, because there is no, perhaps there is nothing happens with our representation as we increase our training budget, right? So, I mean, this can be applied in many different situations.
Thank you for your lecture. That's interesting that among different models there is a delta in intrinsic dimension of LLMs and human text. But as I understand, this is a point-in-time comparison, so you consider the latest models. But I'm wondering whether over time LLMs will develop to an extent that there will be, the text will be less flat and more complex and more similar to human text. I was wondering if you compared how this delta changes over time as LLMs develop.
Yeah, it's an interesting question, but is in fact as LLMs become more complicated, the tools to detect the output is also become more and more complicated. So based on this approach, some more complicated things can be developed, and they can detect sometimes even better. So this is one of the directions to develop further, rather, in this case. But interestingly, for example, with the case of GPT-type models, it seems that the output contains very often some kind of pattern that the researchers put there intentionally, so that the component that produces it can distinguish the output text. So we see this also by our methods. So there are some injected patterns into the generated text. And in a sense, it becomes even more simple sometimes. Okay.
Okay, thank you, sir. My question is similar to this last question. In your explanation of intrinsic dimension detectors, you said that the AI-generated contents has what do you call it, a lower, instinct dimension. So is it because it's, yeah, slide.
Yes.
Yeah. So it has like a lower intrinsic dimension. So while the human-generated contents, it's have what do you call it, higher. So do you think all the models will improve, or is a fundamental issue of the autoregressive generation?
Excuse me, can you repeat your question?
I think in your explanation, you said that the AI text clusters are more tightly, which have lower dimension,
Yes.
right?
Yes.
While the
Yes.
human-generated ones would have a higher dimension. So is that a fundamental problem, or do you think as the model, what do you call it, develop, or it can be this issue, the gap can be a bit closed?
In a sense, it closes, but as I said, based on this approach, we develop further methods that works good. So, studying language models representation from topological viewpoint or from geometrical viewpoint permits to distinguish still. And sometimes, as I said, with the development of the models, because of the injected patterns, this can be even easier with the development of the models. Yes.
Thank you. I wanted to ask if we compare two different neural networks and somehow their RTD comes close to zero, can we say that they perform almost the same?
No,
or not?
I didn't say that, but I said that it can be an indicator that we don't have to spend more budget, yes, on training. Just an example of application.
Thank you very much for so interesting talk. So if you, for example, consider my brain as LM, can we measure its intrinsic dimensionality or probably topological divergence if, for example, you can ask me any question? And
I don't know. It's an interesting question. I believe, I don't think I've seen many studies of this, but yeah, studying the representation of knowledge of inside our brain is definitely exciting subject. Yes, but I don't think I've seen.
How would you evaluate? Is it theoretically possible or not? I mean, suppose so. If we have the black box and we can ask any language question to this box, and we are allowed to ask, I don't know, let us say infinite number of questions. Mathematically speaking, is it theoretically possible to evaluate intrinsic dimensionality of the underlying network? Or
yeah, you can put it. You can put it into, like we did, like a Roberta language model, and study text generated by the brain as a text, and study intrinsic dimension of this text. But to what extent this reflects representation in our brain, this is another question. Probably if you, to some extent, it gives us some notion of what it can be, but probably text or spoken output does not capture all dimensions. That's the question, whether there is a discrepancy between spoken language or the written language. Certainly there are, by the way, between spoken and written, and probably there is some discrepancy between our inner thoughts, which can be not necessarily expressed in a language form, right? They can be some kind of abstract form, abstract thinking, you know, like, I don't know.
can we run probably a simple experiment using this Roberta setup, measure it before sleeping and after sleeping? Simply check if intrinsic dimensionality is increased after sleeping?
I don't know. It's a setup I've never considered. Probably the most interesting that while you're sleeping, yes, but yeah, sure, all this is exciting domain. One can probably try to think of some experiments using the spikes inside, the electric spikes, measuring electric spikes inside our brain as well. So to what extent we can measure the dimensionality of the representation. But whether there is some correlation when we measure such dimensionality and the language dimensionality when the person speaks. I mean, all this is very exciting, but I've never seen any. Well, there were some works that use IRTD in this setup, but not in the sense that you mentioned. Yeah. Okay. Thank you for your attention.